Thank you so much for hosting me here. I'm having a wonderful time. We could have saved some time if we would have referred to my roots, which I mentioned as I went on a private jet a few months ago to the Pacific Ocean. The pilot greeted me and said, "Welcome aboard, Professor Loeb." And I said, "We don't need titles here. You can call me Avi, because fundamentally, I'm a curious farm boy." I was born on a farm, connected to nature, less so to people. And what I really want to know is, are we alone? Or is there an intelligent species out there? I think it's arrogant of us to assume that we are unique and special, because there are billions of stars with planets like the Earth, roughly at the same separation. We know that now. And moreover, most stars formed billions of years before the sun. And we sent 5 probes to interstellar space out of the solar system. There were Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons. Just over 50 years. And we had 100 years of science and technology that allowed us to do that. So just imagine another civilization that preceded us by 1 billion years. It would have taken those probes less than 1 billion years to cross the Milky Way galaxy and arrive at our doorstep. Is there any package in our backyard? And it sounds to me like common sense, but common sense is not common. For the past 70 years, we've been searching for radio signals. And that's just like waiting for a phone call. You're out of luck if nobody calls you when you're waiting. And 70 years ago, Enrico Fermi asked, "Where is everybody?" He was at lunch in Los Alamos. I find that very pretentious because he didn't even search. He didn't look through telescopes. And we all know that, if you're single and you're at home and you say, "I don't see any partner around me," well, the advice is, go out to dating sites, look through the windows, go out of your home, basically, and you might find someone out there. So a lot of people that have an opinion on this matter are not seeking evidence. And since this is a science library, I wanted to emphasize that it's all about evidence. It's not about opinions. As much as they may have many followers on social media, that's completely irrelevant. When Galileo said the Earth is not at the center of the universe, it was not a matter of popularity. The Earth continued to move around the sun even when he was put in house arrest. And the same story repeated with continental drift. The continents continued to drift even though the most distinguished scholars at the time ridiculed the idea for 50 years before it was accepted. So the issue is evidence, that's all. And that, I started as a theoretical physicist for decades, and the last year was mostly about leading an experiment. And maybe it's a sign of age. I was attracted to ideas at a young age, and now I realize if others are not seeking the evidence, I should seek it. So that's what my book talks about, and also the question of whether we are alone is the one that will transform society for a variety of reasons. We will learn from a smarter kid on our cosmic block. We can learn about our technological future, and we can also be inspired to explore space. We are investing $2 trillion every year in military budgets. And just imagine changing priorities, listening to the words of John Lennon. Imagine all the people living in peace. If that were the case, we would have a surplus of $2 trillion a year. What can we do with it? Well, Within 1 century, we can send a probe towards every star in the Milky Way galaxy. Just 1 century. Billions of those probes. And maybe someone else was intelligent to that level, and they reached our doorstep. And we just don't check. And we just argue that everything in the sky near Earth must be stones. I call that the Stone Age of science. So, to explore this question experimentally, a couple of years ago, I decided to lead the Galileo project. It was during the pandemic. Several multi-billionaires came to the porch of my home and offered funding. I did not do any fundraising. In fact, it's interesting because the preceding decade I was chair of the astronomy department, and we wanted to get funding for a telescope that we were partners of and worked very hard at it and didn't get much traction. But after I published my book, Extraterrestrial, people started showing up on my porch, and I realized, maybe it's all about the vision, not about doing something that others are doing. So, what is the Galileo project? What we have as of now is an observatory, completely new observatory, to look at all objects in the sky. And you might say, well, there are astronomical observatories, but the problem of the existing astronomical observatories is that astronomers focus on very distant sources of light, and they look at small portions of the sky at any given time. So if something flies overhead, like a bird, they ignore it. And we built from scratch an observatory that looks at the entire sky 24/7. In the infrared, optical, radio, audio, and the data is fed into a computer system where we use machine learning software to figure out what we are looking at. Are these natural objects like birds? In which case, I don't care so much about what we see. I would be glad to deliver the data to a zoologist. Are these drones, balloons, that say made in China on them? Again, I find that very boring. Anything human-made is boring as far as I'm concerned. I just want to know if there's anything from outside of this earth. So let me show a brief video that illustrates what kind of instruments we have.
Welcome to an overview of the Galileo project's development site, codenamed Pigeon Run. Our instrumentation suite consists of both wide-field and narrow-field sensors. Wide-field sensors are used for target selection and tracking, while narrow-field sensors gather higher resolution data on potentially anomalous objects. Our main instrument is DALEC, a hemispherical array of 8 infrared cameras. Next to it is the ALCOR, a secondary high-resolution optical all-sky camera. Together, these instruments continuously monitor and track objects in the sky, analyzing them in real time for potential anomalous activity. This is AMOS, our acoustic monitoring omnidirectional system designed to detect and record acoustic signatures across the infrasonic, audible, and ultrasonic bands. AMOS also houses an ADS-B antenna for logging aircraft transponder data, allowing us to quickly separate known from unknown objects. Here we have Skywatch, a multi-static passive radar system designed to detect and track multiple objects simultaneously, measuring object positions and kinematics. Pac-Man is an environmental monitoring system for measuring local weather conditions. Sensors include an anemometer, temperature and pressure sensors, a particle counter, and a flux gate magnetometer. Next up is Spectre, a radio spectrum analyzer with a wide band antenna for measuring radio and microwave emissions. Beacon is currently our only narrow-field instrument. Beacon is a high-resolution pan-tilt zoom camera capable of 40 times optical zoom. Our instruments collect a wide range of data, all of which is fed to our computing enclosure housed beneath the DALEC and ALCOR instruments. Here, data is processed and analyzed in real time. Objects detected and tracked by the wide-field instruments are localized in 3D space and analyzed for unusual characteristics. Selected targets are then sent to the Beacon PTZ for follow-up observation. Finally, data is recorded to disk and uploaded to the cloud via Starlink. These combined systems comprise the current version of the observatory class system, with many refinements, additions, and upgrades scheduled for near-term implementation at Pigeon Run.
So you might ask, why do we do that? Well, there was a public hearing at the US House of Representatives in July, in which two pilots gave testimonies about objects that looked weird, that they cannot really figure out. And obviously that was anecdotal. They happened to be at the right place at the right time to see something unusual. What we are doing is systematic. We are monitoring the sky all the time. We'll make copies of these observatories and place them in many locations and get to the bottom of what are these unidentified anomalous phenomena. And if it ends up being either natural objects like birds or human-made objects, so be it, then we can move on. And obviously for the government, it's a matter of national security. The Galileo project is the only scientific project doing that right now. And there was a study by NASA recommending that scientists get engaged. So we are planning to put it in various locations within the US. There will be a copy of the system at Harvard that is now being assembled in Colorado, and we plan to make more copies depending on funding. Each of these observatories is a fraction of $1 million. So it's not very expensive, and there are, of course, opportunities for naming each observatory after the funder. So one more thing we are doing is actually using data from satellites that are owned by, that are publicly shared by Planet Labs. And that allows us to see objects from above, not just from below, and figure out how unusual they are. And we have a plan for expanding the instruments we are using, for example, using multiple cameras at different locations so that we can triangulate and figure out the distance of an object, and then, of course, also developing software. The important point is that humans are not reliable detectors. That's a point that is often missed when people take photos of unusual objects in the sky. The thing is that the Women's Soccer World Cup demonstrated that FIFA doesn't trust humans. They use video cameras to figure out if there was a goal. And that's the way science is done. And we all know that in car accidents, when many people are involved, they give very different reports. So the way science can advance our knowledge is by using instruments that do not have a personality or ulterior motives and analyzing the data. And that's the approach we take. So we have 8 papers describing those instruments. But my interest in the subject came from a different object. That was spotted by a telescope in Hawaii in 2017. And it was given the name Oumuamua, which means a scout in the Hawaiian language. This was the first reported object that came from outside the solar system. It came near Earth and was flagged as a near-Earth object, but was moving too fast to be bound by gravity to the sun. And to me, that was intriguing because a decade earlier, I predicted in a paper that there wouldn't be any such objects discovered by this telescope in Hawaii. And based on what we know about the solar system and assuming that all the stars in the Milky Way are similar. So we just didn't expect a rock to be detected by this telescope, and yet it came. And then as time went on, more data was collected on it, and it looked weird. It didn't look like an asteroid or a comet of the type that we're familiar with in the solar system. For example, as it was tumbling every 8 hours, the amount of light reflected from it changed by a factor of 10. And interpreting that meant that the object is flat, like a pancake. And then it was pushed away from the sun without any evaporation. So there was no rocket effect from a cometary tail behind it. And so the question is, what was pushing it? And I suggested that it's just a thin object pushed by reflecting sunlight. And nature doesn't make such objects. Maybe it's a surface layer of a bigger object manufactured technologically by another civilization. And actually 3 years later, there was an object which imitated the qualities of Oumuamua. It showed the push away from the sun as a result of sunlight reflecting off it, no cometary evaporation. And then the astronomers who discovered it in Hawaii realized within a few weeks that it was actually a rocket booster that NASA launched in 1966, minding its own business and just noticed by the telescope. And it was made of stainless steel, that's why it didn't evaporate, and it had thin walls, that's why it had a large surface area for its mass. So here you have it, a technological object, because we know that we produced it. The question is, who produced Oumuamua? And that's what led to my interest in the subject as an astronomer. And then, it's jumping. 2 years later, I was interviewed about a meteor that was spotted over Kamchatka. And I went online to read some data on meteors, and I found a catalog that NASA compiled over the past decade with 273 objects, including velocity measurements by the US government. And I asked my student, Amir Siraj, why don't you check whether the fastest moving objects, just like Oumuamua, might have been unbound to the solar system. And sure enough, we found an object from January 8, 2014 that collided with Earth. It was 0.5 meter in size, and as a result of its friction on air, it produced a fireball with 3% of the energy output of the Hiroshima atomic explosion. It was spotted by US government satellites, and they measured the speed that was way above the escape speed from the solar system. And in fact, we calculated that outside the solar system, it was moving at 60 kilometers per second. So usually cars in the highway move at 60 kilometers per hour. And this object was going across a distance that a car makes in 1 hour. It was doing it in 1 second. That's faster than 95% of all the stars in the vicinity of the sun, relative to the local frame of the galaxy, the local standard of rest. So it was moving really fast. And the other thing we calculated was based on the government data. It was actually able to maintain its integrity down to the lower atmosphere, and it was tougher than all other meteors in the NASA catalog, 272 of them. So that raised the possibility that maybe it's a Voyager-like meteor. Just imagine Voyager leaving the solar system and colliding with a planet like Earth in the future. It would appear as a meteor of unusual material strength and unusual speed. So to check this out, what it was, in this case, I had an opportunity to go there to the meteor site and look for anything left from this object, unlike Oumuamua that left our vicinity and we can't see it anymore. So I decided to lead an expedition, and fortunately, a few months after announcing it, a donor came forward and offered $1.5 million to go ahead. And so we went to the Pacific Ocean. Let me show you. It was on a ship that was fittingly called Silver Star. And so let me show you a video.
In my silver star, thinking I am one, where you are, drifting in my silver star, thinking I am one, where you are, drifting in my silver star, thinking I am one, and where you are, drifting in my silver star, thinking I am one, and where you are.
So this expedition took place between the 14th and the 28th of June this year. And it all resulted from the recognition that there was this object from 2014. We wrote a scientific paper about it, and the paper was not accepted for publication because the reviewers argued, we don't believe the US government. And by the way, this is the US Space Command, which gets more funding than NASA, and reports to the president about any ballistic missile coming from North Korea. So it's quite arrogant on behalf of astronomers to say they don't know what they're talking about. Nevertheless, I was at the time chairing the board on physics and astronomy of the National Academies, and I was frustrated by this, and at dinner I mentioned it to a number of colleagues, and one of them said, let me help you, and it ended up with a person from the White House reaching out to the US Space Command, and within 3 years, because government works really slowly, in March 2022, they issued a formal letter from the Department of Defense to NASA, in which they confirmed at the 99.999% that this meteor came from outside the solar system based on its speed. So the Department of Defense came to my defense, and the paper was accepted for publication. And at that point, the government also released some data about the fireball, and that convinced me to lead an expedition and search for the relics of this object. And so the fireball of this object showed 3 flares separated by 1/10 of a second from each other, and they occurred less than 20 kilometers above the Pacific Ocean. And we calculated that the stress on this object just before it disintegrated was far greater than even iron meteorites can sustain. And so this was an unusually tough object. And the Department of Defense provided an error box for the location of this explosion, which was 7 miles in size, quite large. The ocean depth is more than a mile at that location. And we decided to survey that region, but to narrow down the likely path of the meteor, we used a seismometer, data, publicly available data from a seismometer on Manus Island in Papua New Guinea, about 85 kilometers away from the explosion site. We were able to pin down the value of the distance to the explosion just from the time delay between the sound and the light. You are all familiar with this experience. When there is a thunder following lightning, there is some delay. And so we used the delay, knowing the speed of sound, to figure out how far away the explosion was and narrow down the path of the meteor to a strip, which you see here in red, within the Department of Defense error box. No. Okay, so this is a team photo of the group of 28 people that I was fortunate to recruit. Some of the best expedition leaders in the world, and they agreed to join me on this. We had exceptional professionals that, each of them was crucial for the success of the mission. We built a sled with magnets on both sides, roughly 1 meter in width. And the idea was to drag it on the ocean floor and collect magnetic particles that were melted off the surface of the object when it was exposed to the immense heat from the fireball that it generated as a result of its friction on air. And the sled was connected with a cable to the ship. And you can see the cable going through this frame behind us. It's called the A-frame of the ship. The cable went out to about 3 miles. 1 mile was the ocean depth, so the sled was dragged behind on the ocean floor, skimming the surface of the ocean. And initially, on the first day, it wasn't sitting on the ocean floor because the cable would lift it up, and it was kiting. But then the engineers on the ship figured a way of keeping it on the ocean floor by going with the ocean currents. So that was a relief. And you can see here pictures of how the sled was brought up to the deck, like in the middle and the right panels here. That's when we took it out of the ocean, picked it up after it went over a distance of about 7 miles for each run. Altogether, we had 26 runs crisscrossing the region. And what you see on the bottom left and middle is me jogging on the ship every morning, just like I do on land at sunrise. I did it every morning. One day, we had a filming crew. I mean, there were 50 filmmakers and producers that wanted to be on the ship. We selected one. And the director came to me and said, can we film you jogging? And they asked me to jog 3 times longer than usual. It was about 9 miles equivalent. There was an anecdote, actually. I was using my workout app and realized that I'm actually sometimes moving slower than usual. I thought it's the jet lag, but then I realized it's actually measuring the speed of the ship, not myself, because of... At any event, the director asked me, he said, Avi, you're running. Are you running away from something or towards something? And I said, both. I'm running away from some of my colleagues who have strong opinions without seeking evidence. And I'm running towards a higher intelligence in interstellar space. So here is the sled. You can see it on these magnets, the round magnets, neodymium magnets. They would collect mostly volcanic ash, black powder, and we would scrape it out and then dry it up and put it under a microscope. And for 6 days, we didn't see anything unusual, no molten droplets that were visible to us until we decided to filter out the volcanic ash, which is made of tiny particles, with a mesh. And then we were left with the bigger particles, more than 1/10 of a millimeter, so the size of a grain of sand. And we started putting them under the microscope. And sure enough, we saw a spheral, a molten droplet from the surface of the object. And I hugged the person who found it first, because that's what we were looking for. And as you will see, they look very distinct from the surroundings. And I realized once we find one, there will be more, because that's my experience in the kitchen. If you see an ant, you get alarmed. So let me show you a video of how the sled went over the ocean floor, and it's just like mowing the lawn. It's mostly muck on the ocean floor, and more than a mile deep, but there is life down there. We saw some shrimps swimming and so forth. We would collect mostly those particles from volcanic activity, but we just didn't know whether there are some additional particles of interest down there. And every now and then we would bump into a rock that you will see in a few seconds and carry it together with us. We would see this picture was taken by a video camera on the sled, attached to the sled, not in real time, but as we brought it up, we would review the video. So we did it 26 times, back and forth. Some of the runs were outside the region of the meteor, just so that we get a sample of the background. And you can see the map of those vessel tracks. Many of the tracks were near the meteor path, but some were very far away, 10 or 20 miles away. And here is a zoomed in image of those runs close to the meteor path, which is shown in orange. Oops. No, that's not good. Okay, so here is an example of how a spheroid looks like, a molten droplet. It's very distinct from the sand in which it was found. You can see the arrow pointing at it. And moreover, there are many others that you can notice in this picture, many of which are smaller. They look like metallic marbles. And this is a microscope image. They're 1/10 of a millimeter to a millimeter in size. And when my daughter saw these images, she asked me if I can put one of them on a necklace for her. And I said, these are too small, you cannot thread them. They're the size of a grain of sand. And here is the delivery room. Those babies that we delivered were tiny particles that we put in vials. These were their beds, and that's the delivery room, like a white basket that carried them. I shipped the materials in this black suitcase to my home through FedEx because I was worried that they may get lost in customs. And they arrived after a few days, but I reasoned that a few days is not a big delay, given that it took billions of years for this material to get to Earth. And actually, the funder is next to me with a black raincoat here on the left. His name is Charles Hoskinson. And this is a picture in the laboratory at Harvard after we brought the material to my colleague Stein Jacobson, who is a world-renowned geochemist, and he has a mass spectrometer. Next to me, you see my summer intern, Sophie Bergstrom, who came to shadow me during the summer. She wanted to become a science journalist, and at some point she asked if she can help with the analysis, and I said, of course. Here is a microscope and tweezers, and we found on the ship 50 spheroids. She found more than 600, and I gave her the title, the Spheroid Hunter. And here are some of the spheroids she found. And these are images we took on the day we came back through San Francisco Airport. We went straight to Berkeley that has a scanning electron microscope. And what we realized, looking at one of the spheroids, is that they are just like Russian dolls. They have spheres inside spheres. So the idea is that the smallest spheres solidified first, and then they were engulfed with liquid iron that glued them together. And here they are, nested on a matrix of dendrites. They look like eggs. And when I came back to Harvard, I asked my postdoc, Laura Domini, to make a map of the yield of spherules per unit mass retrieved from the ocean floor. And what you see here is the map. She basically pixelized the survey region. Each pixel is roughly half a mile in size. And the purple color indicates background, which is a relatively low yield of spherules, whereas the yellow regions are high yield regions, twice as much spherules per unit mass retrieved. And we found 3 yellow regions close to the meteor path. So that indicated that we were at the right place because there was an excess of spherules along the meteor path. And here is an example of one of them that looked like a soccer ball. Another one that looked like a merger of 3 spheres. And that one was particularly interesting because it was big. And so it was also in a yellow region. So we analyzed it first in the laboratory. And here is the composition that we found. So what you see here on the horizontal axis are elements from the periodic table, starting from lithium on the left, going all the way to uranium on the right. And the number 1 here represents the standard for solar system composition. These are called chondrites that represent the building blocks of the solar system early on. And if the object was from the solar system, then we would expect the spherules to have an abundance pattern around 1. But what we found is what you see in red. Elements like beryllium, lanthanum, and uranium are enhanced by factors of a few hundred to 1,000 relative to the standard solar system abundance pattern. So we called this composition Belau. Stein Jacobson came to me and said, I've never seen anything like it. We must give it a new name because it was never reported in the scientific literature. And that's an independent piece of evidence that the object came from outside the solar system, because you don't see this abundance pattern on Earth, the Moon, Mars, or asteroids. And so besides the clue that we had about the speed of the object, now we found those Belau spherules along the meteor path. And here are 5 of them that we isolated. So far, we analyzed only 10% of all the spherules. So we have work to do, but we already submitted a 44-page long paper for publication about the results. And it's very exciting. And the question is, where did these spherules came from? And one possibility is they originated in a planet outside the solar system that had a magma ocean. The rock on the planet was molten, and it had an iron core. And then some elements that have affinity to iron would settle to the core of the iron core and leave behind those elements that we found pronounced in the spherules. The Earth started as a magma ocean, molten lava, as a result of bombardment by big objects that collided with Earth, one of which produced the Moon. The Moon also started as a magma ocean, and the same is true about Mars. But what you find in the crust of these objects right now is not the same as what we found. So it must have been a planet of this nature around another star. That's one possible natural origin for these spherules that came from the surface of the meteor. But it's also possible that these particular elements were selected for a technological reason. Some astronomers suggested to me that lanthanum and molybdenum are very good substrates for semiconductors. So imagine molten droplets from semiconductors or computer screens. They will have an enhanced abundance of rare elements. And to find out whether it was technological or natural in origin, we are planning the next expedition in the coming year to look for bigger pieces of the object. Because when you see a big piece, you can tell if it's a rock or a technological gadget. A gadget may have buttons on it. And in my class at Harvard, I asked the students, if we find a gadget with buttons on it, should we press a button? And half of the class said, no way, don't do that, it will affect all of us. And the other half said, yes, please do, because we are curious to see what would happen if you press a button. And then one of the students said, and what would you do, Professor Loeb, given this split vote? I said, I will take it to a laboratory and examine it before engaging with it. So we should see if we find a piece of rock or a gadget. That's for the next expedition. We also analyzed isotopes of iron and realized that they have a ratio very different from terrestrial rocks, the rocks on Earth. So it definitely did not come from Earth. And volatile elements were missing in those spherules. These are elements that get evaporated during an airburst. So another clue that these spherules came from a meteor from outside Earth. So there are many interesting clues, but we are just at the beginning of analyzing what we found. And altogether, I think the important lesson is that it's worth taking risks in science, because sometimes you might be successful. Obviously, if you don't search, you will not find anything. And being an optimist is a good approach, because sometimes life is a self-fulfilling prophecy. So by being an optimist, you promote a better future. This expedition was risky because there were many failure points. For example, I could have imagined the expedition, but nobody would come forward to give the money so that it's realized. I could have not been successful at recruiting the best professionals in the world to take part in this expedition. Also, we could have built a sled that would not work, or the meteor could have been too small to produce enough spherules for us to find, because we had a very small sled going back and forth across a very big region. And even if we collected those spherules, we might have not been able to isolate, to identify them. And even if we brought those spherules back, Stein Jacobson could have told me, you know, I'm busy with other projects. I don't have time for you. And instead, he allocated his entire research team to this. So I was quite fortunate. I feel really lucky to have been able to pursue all of these milestones. And the fact that we were successful feels like winning a soccer match, or it's just a team effort, and it's the best experience I had in my scientific career, only a few months ago. And now, of course, I mean, this is a picture from the end of the expedition when Art Wolf, who was a commander of a destroyer during the Vietnam War, he's 85 years old, standing next to me. I really admired him because everything he said was right. And all of his expeditions were successful in the past. And we were planning the next one to look for bigger pieces, as we were looking at the sunset after having champagne that we found something. So that's it. For details about the planning of the expedition and what the implications might be for humanity if we ever find a technological package near Earth, check out Interstellar. Thank you very much.
All right, raise your hands if you have questions. I'll come by with the microphone. Just be sure to hold the microphone close to your mouth. Before we go to Q&A, though, how many of you would push the button? It's probably about half. All right, we'll start here.
I wanted to encourage young people also to ask questions. Yeah.
I have two questions. One is, given the data you observed from the Department of Defense satellites, are you able to extrapolate the approximate origin of this material? And then number two, I read your paper, the preprint, and it goes to a great deal of detail on the chemical analysis. Oh, isn't that something? I just forgot my question.
Let me answer the first.
Oh, the age. Are you able to determine the age of the material?
So the two questions are related because on the ship I realized that this is a new frontier where we explore what lies outside the solar system with microscopes rather than telescopes for the first time. And never before was an opportunity of that nature. So if we can use radioactive isotopes as clocks, which in principle is possible, for those isotopes like uranium 235, 238, or thorium. Interestingly, uranium 238 has a half-life equal to the age of the solar system. And thorium has a half-life equal to the age of the universe, just by chance. So these are good measures of the duration of the journey. And if we could tell how long the journey took, since we know the velocity of the object when it entered the solar system, you multiply the velocity by the duration, you get the distance of the source. And you can look at that location, at that distance in that direction, and find the stars that were there at the time that this object left them. So that's something new that was not possible before. And as of now, we haven't measured the age yet, but we are now in the process of looking at isotopes. In fact, just 2 days ago, we had a meeting in which this was discussed, and we're looking forward to finding those isotopes and analyzing the age from that. So yes, in principle, we can do what you just mentioned.
Right, we have a question here about midway back in the room.
Were there any unknown elements discovered in the material?
We are unable to search for unknown elements. I mean, the periodic table is complete with respect to elements that we know, that we found so far in the solar system, or even in the interstellar medium. You know, we see spectroscopic transitions, I mean, the fingerprints of all the elements, and they always match what we already know. But in principle, you could find some particle that we never saw in the solar system. For example, we know that 83% of the matter in the universe is of some unknown substance. It's called dark matter. And we've never seen it in the solar system. And obviously, if you would ask those people who focus on stones in the solar system that say everything in the sky is stones, they would argue the data on the dark matter must be wrong because you can't fit it with stones. But the truth is that it's a whole frontier in cosmology, trying to figure out the nature of dark matter. And so if this meteor had some component of matter that we are not familiar with, I would not be able to notice it because our instruments are designed around the kind of materials that we are familiar with. So I wouldn't rule it out.
Professor Loeb, here on your right.
So if you found it was actually technology, would there be a way to communicate? Would you try and find a way?
Yeah, so that's an excellent question. First, one has to realize that the distances between stars are huge. So the nearest star system is Alpha Centauri, which is 4 light years away. And it takes light 4 years to get there or back. So you need to be patient. If you send a message, you will get a response at best after 8 years. But this is the nearest star, and most stars are tens of thousands of light years away from us in the Milky Way galaxy. So you have to wait tens of thousands of years. So it's not practical, and that's why it was never urgent to figure out a protocol. If we receive a radio signal from, if we listen to I Love Lucy from another civilization, and by the way, I Love Lucy went out 74 light years by now. There are hundreds of stars maybe that it could have listened to it, but it's not a lot. And so, but you can get good royalties if you wait tens of thousands of years. The issue, so a better approach is actually to look for any letters in your mailbox, right? Any packages. Then you can read off the postal address of whoever sent it and send something back. But that again takes even more time because the speed of our spacecraft is about 10,000 times smaller than the speed of light. So for the spacecraft that we produced so far to reach Alpha Centauri would take 50,000 years. The amount of time, I mean, they should have been sent when the first humans left Africa for that spacecraft to arrive now to Alpha Centauri. So that's the nearest star. So that's why we can most likely just learn about them before, without replying or doing something about it. And the other lesson from that is it doesn't make sense to send humans or biological creatures to an interstellar journey because it's a very hazardous environment. There are cosmic rays. A human body cannot survive more than a year and a half in space. So I don't know why Elon Musk dreams of dying on Mars. That's not a good strategy. If we ever go to Mars, it would be much better to go into a cave. These are called lava tubes that you can find also in Hawaii or on the moon. So we started in prehistoric caves, and if we go ever to Mars to have a community of people, we will go underground again because cosmic rays cannot penetrate the ceiling of the cave, and also the temperature variations between day and night will be moderated if you. So actually, I'm most curious to send a drone into a cave on Mars and check whether there are any prehistoric paintings on the walls. But because Mars lost its atmosphere just a few million years ago, a few billion years ago, and that's if life was accelerated, like intelligent life arrived at Mars twice as fast as it did on Earth, then there could have been intelligent beings on Mars as well, before it lost its atmosphere and liquid ocean. So the answer to your question is, we better, if we ever want to reply or send something, we better use technological gadgets. And that includes probes that are not waiting for our guidance. So far, we put robots on Mars. These are the Perseverance robot and the Ingenuity helicopter. I call that, these are managed by engineers in Pasadena, in the Jet Propulsion Lab, and I call it helicopter parenting because we are managing a helicopter. But you can't do that with interstellar travel because it takes so much time for the signal to go back and forth. So you need a probe that is intelligent, that can decide on its own without waiting for guidance from the sender. And the way to do it is with an artificial intelligence brain. And we haven't sent AI systems to space as of yet, but that will be the future. So now reversing it, what I expect to visit us, if it's functional, would be AI astronauts.
All right, Professor Loeb, back here, way at the back of the room.
Okay.
What are your thoughts on the risks of making contact with a civilization with far advanced technology?
Right, so there are two things we might find if we search the vicinity of Earth for objects. One is space trash. Just imagine Voyager leaving the solar system. It will not be functional in 10,000 years once it leaves the solar system. So we are polluting interstellar space with trash, and over billions of years, everything produced by other civilizations kept accumulating in space, just like plastics in the ocean. By 2050, there will be more mass in plastics in the ocean than fish. So be careful when you go to a fish restaurant. And you know, so that may be the most common thing for us to find. Space trash, it would, even though it's not functional, it could still inform us about the technologies that were used. But there could also be functional devices, and from them we can learn much more, because it's just like having a visitor in your backyard. There is no point in establishing committees to decide about protocols on what to do with a visitor, because our imagination is limited to what we encountered on Earth. And nature is much more imaginative than we are. So it's better to wait, and then when we see a visitor, to figure out what it's seeking and what its intent is, and only then decide how to respond to it, if we are dealing with a functional device. And I prefer not to imagine, because you know, when you go on a date, you don't want to imagine what you see in the mirror. It could be better than that.
All right, Professor Loeb, let's get to a couple of questions from our online viewers, and thank you for tuning in throughout the world. One question is, can your observatories detect near-Earth asteroids?
No, the Galileo observatories that I described look at objects out to a distance of about 5 kilometers, because otherwise they're too faint for us. They're too far away, so the cameras that we have cannot see beyond that. For near-Earth objects, there is a Rubin observatory in Chile that will start operations in 2024, and it will have a camera that has 3.2 billion pixels. That's 1,000 times more than the camera on a cell phone. And it will survey the southern sky every 4 days. So we are likely to find Oumuamua-like objects every few months. And having the Webb telescope now look at such objects from a different direction than telescopes on Earth would allow us to pinpoint their distance and motion in 3 dimensions to an exquisite precision. And also the Webb telescope will measure the heat emitted by those objects, and we could infer their size, the reflectance of these objects. We will have much more data than we had about Oumuamua. So the Rubin Observatory is the answer to this question.
All right, another question from an online viewer. How does the profile of elements in the spherules compare to the elements that were used in our space probes, for example, the Voyager spacecraft?
It's very different than any human-made materials, and also from some people were worried about the fallout from nuclear explosions. It's very different. The thing that comes closest to this pattern is a composition that was found on the moon, but it's not the same. I'm currently working on a scientific paper trying to find a natural environment in astrophysics that could give rise. The challenge is that you need 10 to the power 23 such objects produced per star in the Milky Way galaxy to have one of them collide with Earth every decade. And if you take 10 to the power 23 and multiply by the mass of this meteor, which was 500 kilograms, you get the mass of the Earth. So you basically need, for every star in the Milky Way galaxy, you need to take the mass of the Earth, melt it, and then break it up into 10 to the power 23 fragments, each of which is about 500 kilograms. Only then you have enough objects such that one will collide with Earth every decade. And that's quite challenging, but we have a scenario that I'm working on right now. And hopefully next time I visit, I can tell you.
All right, we need to start the book signing soon. Let's do one more question. I know you've had your hand up for a little while here. Let me come around to you.
I'm wondering if you've done the scientific control to see, are these spherules found elsewhere in the ocean or even on land, that there shouldn't be any other recently arrived, and say, well, there might be old ones, so that the related question is, can you say how long they've been on the Earth?
Yes, that's an excellent question, and indeed we decided to visit control regions during the expedition in order to find out what one finds in that region that has nothing to do with the meteor path. So we have that, and the special type of spherules, the Belau spherules, were found only in those yellow regions along the meteor path. So that's the first thing. But moreover, in the scientific literature, you know, there are lots of papers written about spherules from solar system meteors, and none of them has this composition. I mean, there are variations around the standard solar system composition, and you know, some rock experts said, oh yeah, there are variations, but if you look at the vertical scale, the variations are usually a factor of 10 or at most a few tens relative to the solar system standard, and we get a few hundreds to 1,000. And this is unique and not seen before in the scientific literature. And you may ask, why specifically these elements? As I said, the differentiation in a magma ocean could produce them, but not in the solar system. And technologically, of course, uranium could be fuel in a fission reactor, and the other elements used for some other technological purpose. But I think the answer to what the origin is will come from a big piece that we might recover in the next expedition.
All right, we'll sneak one more question in here, the back of the room on your right.
Thank you so much for coming. I was thinking, you know, perhaps I'm thinking a bit too simply, but with all those different elements inside of those spherules, and considering that it came from a small object that streaked through the air at that speed, with different ingredients in a cake, you put it in an oven, those elements change into something different. So I'm wondering, when it strikes the sea, some of those things may be different from what initially fell down. I mean, lead, you mentioned, is very volatile, so it would have burned up in the Earth's atmosphere. Right. But what about thinking about a recreation of the exact conditions would have led to the transformation of that fragment and the resulting spherules? What have we done to try to recreate that incident?
Well, that's an excellent idea, and in fact, I was thinking about it, just like in a case of a cake. When you have a recipe, you can take the ingredients and put them together, but it depends how you put them together and also how you apply heat. You can get very different cakes as a result. So this is something we might do, that we now have the ingredients and put them together and see what, it's quite possible that the high material strength resulted from this combination of elements in addition to iron. And we planned, and of course, if we get a big piece, that would be much easier to figure out. So yes, that is something we plan to do. I even thought about doing it on the computer with, now there are you know, quantum computers that can mimic with AI the properties of various alloys, and maybe we can do a simulation of that. But definitely it's something we plan to do in the next phase. And for now, we are planning to study all the spherules we have to find, you know, whether indeed those Belau spherules are only along the meteor path, as we found so far, and then find bigger pieces. That would be the adventure that I'm looking forward to. So it's all about evidence. That's what I wanted to highlight. A lot of people have opinions, even after we found this material. And on the way back, there was a scientific paper published in the Astrophysical Journal arguing that this meteor must have been made of stone, and the velocity that the government measured must have been 3 times smaller. And just because otherwise their model for stones does not fit the data. And So the one thing I really need to emphasize again and again is that there are people who have opinions on both sides. There are people who are believers in unusual objects near Earth without having the evidence for that. There are people who are ridiculing the search within academia and not engaging in looking for evidence. And both are wrong because science is guided by evidence. And you know, whatever we find, we put out openly, and it's just a matter of time until we realize what is there, you know, near Earth. And even though such objects collide with Earth once per decade, if you do the math, there are millions of such objects within the orbit of the Earth around the Sun right now. We just cannot see them. They are half a meter in size and they don't reflect enough sunlight. And so the only way to see them is when they collide with Earth and produce a fireball. And perhaps one way to figure out what their nature is to go out and find more of them, even before they collide with Earth. So it's all around us, and we haven't looked. Only over the past decade, we found the first interstellar objects. This meteor was the first one, 2014. Oumuamua was the second, and both of them look different than asteroids or comets that we are familiar with. So that, to me, is intriguing and exciting, and let's see what we find as we move on.
Thank you, Professor Loeb.